All right, so for section 5.3, we're going to discuss inverse functions. All right, so a function g is the inverse of the function f when these two things happen. So when we plug g of x into the function f, we get out x, and when we can plug the function f into the function g, and we also get out x. Okay? So that would be examples, or that's the definition of an inverse of a function. Okay. All right. So now we have just a couple important notes here. So if g is the inverse of f, then f is also the inverse of g. Okay. So the relationship does go both ways here on f and g. All right. The domain of f inverse, and we denote inverse with that little to the negative one. The domain of the inverse of f is the range of f. And it is the same for function g also. Okay. Well, listen, I don't want to say same for g. It would be the vice versa. So if the domain of f inverse is the range of f, then the domain of f is the range of f inverse. Okay. And then the last thing here, if a function has an inverse, the inverse is unique. Okay, so that means that there's only one. So the inverse would be unique. Okay. All right, so now that we've kind of laid out the definition of what an inverse is, let's just look at some simple examples, and these will make sense to you. Okay. So just as an example, say we have a function f of x is x plus c, then the inverse of that function is x minus c. Okay. Because if I plug in 1 into the, so let's say I do this. Let's say I solve f prime, I would do this. So I'm going to plug x minus c into the function x plus c. So I have x minus c plus c. Well, of course, minus c plus c just leaves me with x. So that's an example of an inverse. Another example would be with multiplication and division. So let's say that f of x is equal to c times x. Then we have an inverse to be x over c, because if I plugged one into the other, then I would end up with x being left, okay? All right, so now let's do a real example of this. Let's say that we have a function of x to be the square root of x minus 6, and then g of x is equal to x squared plus 6. Okay, and we're going to restrict that x is greater than 0, greater than or equal to 0. Okay, all right. So all I have to do is test this out in both directions. So I want to plug g into f, I want to plug f into g. Okay, so f of g of x, so I plug g in, I get x squared minus, or x squared plus 6 minus 6. Well, that's of course just x squared. Square root of x squared is x. Okay, and then I want to test to see if it's the same way in the other direction. So I'm going to take x minus 6, the square root of x minus 6, plug it in to square it, plus 6. I square the square root, that leaves me with x minus 6 plus 6, and that of course equals x also. So it is sufficient to say that f and g are inverses. Okay. So that would be how you could test to see if a line is an inverse. Okay. All right. Now we do have another test that we want to be able to employ, and that is the horizontal line test. Okay, you all are all similar or all familiar with the vertical line test. All right, so it does work the same way, but we use the horizontal line test to see if a function is 1-to-1. Okay, so we see if a function is 1-to-1. So just as an example here, I'll just draw this. Okay, so I take my horizontal line, test it out a few places. That function is 1-to-1. Okay, an example that would not pass would be something that does this, right? Horizontal line, it touches at 2 places, so that is not 1-to-1. Okay. All right, so being able to see if a function is 1-to-1 is very important. And then the other thing that we want to be able to look at is to see if a function is monotonic. Okay. So monotonic just means that it is increasing or decreasing across the entire domain. Okay. So a function is monotonic if it just does something like that. Okay. So as long as it's continuing to go up or down, increasing or decreasing across the entire domain, then it is monotonic. Okay. All right. So, well, why would these be important in using inverses? Okay. Well, this leads me to theorem 5.7. Okay. And the first part of this theorem says a function, and I'm going to use fn for function, has an inverse if and only if, so IFF is if and only if, it is 1-to-1. Okay. So we have to be able to test to see if it's 1-to-1 first before if we can know if it has an inverse or not. Okay. The second part, if f is strictly monotonic, then it is 1-to-1 course, we could validate that by using the horizontal line test. And then has and therefore has an inverse. Okay. So that's just two easy ways to know if a function has an inverse first. Okay. Before you want to know or want to even test to see if you can find an inverse for it. Okay. All right. So let's look at a function like this. Let's say f of x is equal to the natural log of x minus 4. Okay. All right. Well, if I don't know what this looks like, and maybe let's just say that I don't have an easy tool, and let's say I'm going to have to restrict x to be greater than 4 because the natural log can't be negative, or it can't take the negative or natural log of a negative. So let's say that I don't have a graphing tool readily handy. So then I could take the derivative, because the derivative is just a slope. Well, I know that the derivative of this is 1 over x minus 4. Okay. And since I am restricting x to be greater than 4, is there ever a place where this would be 0, because then that would mean the slope was 0? Well, that can't ever happen. And is there a place where the slope ever goes from positive to negative? No, because x is always going to be larger than 4. So 5 minus 4 is 1 over 1. 6 minus 4 is 1 over 2, etc. Okay, so then the function f of x, is strictly monotonic and has an inverse. Okay. So that's a good way to be able to tell if a function has an inverse. Okay. You can just look at the graph, of course, but in as far as calculus 2, we don't want to be basing all of our assumptions on the graph. We would rather be able to do the calculus part to be able to justify our answers. Okay. So now, how do we find an inverse? So that's kind of the big part of this section, is just being able to find the inverse. Okay, so I'm going to show you how to do that. All right, so first we need to make sure that the inverse exists, which we just talked about that. Does the inverse exist? Well, if I can get that to erase. Yeah. Well, we'll just pretend I didn't spell that wrong. So that is theorem 5.7 that we use to justify that. Okay. The second thing we're going to do is we're going to solve for x as a function my eraser isn't working. All right, solve for x as a function of y. Okay. Then we'll interchange x and y. We'll define the domain. Okay, so we will define the domain. And then the last thing is we'll verify. All right, and to verify what we're checking to see, okay, when we plug one into the other, do we just get x out? Okay. Okay. All right, so these are the steps that we're going to use to be able to find if it has an inverse. Okay. All right, so now I have my inverse function. Okay. And I don't have to worry anything about defining the domain aspect because no matter what, it's always going to be positive here, so it's not going to change anything. But now I just want to verify by plugging the inverse back into the original function. And I should get out x after I simplify. Okay, so I have x squared plus 9. I have the square root of that squared minus 9. Of course, when I square it, the square root goes away, so that leaves me with x squared plus 9 minus 9. Well, of course, that's just the square root of x squared, and that is just x. All right, so I am verified in this direction. So now I want you to verify it in the other direction, and it should work just fine. Okay, so that is for you to do. But this concludes section 5.3. If you have any questions, please feel free to email me. And as always, have a great rest of your day.